Hello, everyone. Today we are going to be talking about probabilities associated with statistics. I know that in the chapter readings for this week, it says that we are going to be covering both chapter 6 and 7 for our lectures, but in reality, we are only going to be covering chapter 6 for the purposes of our class. Chapter 7 from our textbook is a chapter that I would reserve for an intermediate statistics class or a graduate level statistics class. So for our purposes, we're only going to be talking about probabilities in the sense of our use and our purposes that we need for understanding basic statistical principles and for also the testing of inferential stats that we're going to be talking about later on during the course of the semester. So for probabilities, probabilities are a concept that a lot of people get kind of really confused about or get a little bit worried about whenever it is that they encounter it, because probability is kind of a difficult thing for us to define, and sometimes we don't really understand what probability is. But when we think about what is a probability is the likelihood of an outcome occurring in proportion to all possible outcomes. So what does that mean for me? It essentially means if I know all the possible alternatives or all the possible outcomes that may exist in a given event, and I want to know what the likelihood of one thing happening out of all of those things, that's the aspect of a probability. What's the proportion? What's the fraction? What is the likelihood of that outcome occurring when I have to consider that there are all these other possibilities or all these other alternatives that may potentially exist out in the real world? So here, think about flipping a coin. That's our easiest example associated with probability. If you flip a coin has a 50% chance of landing on heads or on tails. Why does it have a 50% chance? Well, because there are two alternatives that may potentially exist. My two alternatives are heads or tails. And if I flip my coin, it's only going to land on one of those possibilities. It's only going to land on either heads or lands on tails. So in this particular instance, if I want to know what the probability of it landing on heads is, I would look at the possibilities of it occurring on heads, which is a value of a 1, because there's only one head on the coin. But there's two possible outcomes that may exist in terms of me flipping the coin, that it may land on heads or it may land on tails. So here we would find the probability or the proportion of the likelihood of it actually landing on heads in that particular instance. So when we think about probability, what is probability? Again, it's this likelihood of an outcome occurring in proportion to all possible outcomes. We essentially use probability as a mechanism that we use for uncertainty. So in other words, when we don't know what may potentially happen, we rely on the aspect of probability or on the concept of probability to kind of give us some idea of the potential certainty that may occur of a given event, which will also give you the uncertainty value in terms of the likelihood of other possible events occurring as well. So ultimately, probability is going to be a value that we can represent as a percentage, that it can be between 0 and 100. It can also be expressed as a fraction or a proportion of all possible outcomes. Normally, we represent probability with the lowercase p, which is italicized. So for probability, it can really be any value that lands anywhere between 0 to a 1. So here, one of the things that you have to consider is that you can change this fraction or this proportion of your p-value or of this probability value to be represented as a percentage. So think of the following situation where we say, well, the probability of our coin landing on heads is going to be 0.50 or what we would call 50%, right? So we have a proportion here, 1 divided by 2, which would be our fraction, which would be 0.5 or 50%, right? So you can represent probabilities as proportions. You can represent them as fractional values. You can represent them as percentages, whatever it is that you would like. But you just have to make sure that you do represent them the appropriate way. So we want to make sure that if we're going to say that it's going to be a fraction, it's going to be 1 divided by 2, or it's going to be 0.5, or that it's going to be 50%, and we have to make sure that we put the percentage sign on there. So when we think about probability, ultimately exists when all scores are allowed to vary in our data sets. So if we don't have a specific score that people can get, then we're going to have this mechanism of probability occurring. So for instance, if I were to say, well, the only alternatives that people can get on the exam are a 1. I'm really not giving you any alternatives. So if I don't give you any alternatives and I'm telling you your score can only be a value of a 1, then there is no aspect of probability because I'm telling you with 100% certainty what everyone's value is going to be. But unfortunately, that's not the case. So unfortunately, for instance, in an exam, I can't say, well, everyone's score is going to be exactly a 74 or exactly a 75, but rather people's scores are going to be allowed to vary anywhere between a scale of 0 to 100, thus giving me so much variability in my scores that I'm going to have to be able to calculate a probability associated with the likelihood of people getting a specific value or scoring in a specific range of values for my particular exam. So when we calculate probability, this is the formula that we use for probability. Probability, which here we represent again with our lowercase p, this is the likelihood of our event occurring, the one that we want, right? So we want the probability of, again, let's say that we flip a coin and we want it to land on heads. So in the numerator of our fraction, we are going to have the number of outcomes classified as our particular event. So in our particular case, let's say, for instance, that we are going to say that we want to know what the probability of our coin is landing on heads. How many heads actually occur on a coin? Well, there's only one head that occurs on our coin, but there's 2 possible outcomes that may exist on a coin. The 2 possible outcomes are the heads or the tails. So in other words, we have a value of a 2. So here, to calculate my probability, it would be a 1 divided by 2, because again, 1 represents the outcomes that I'm classifying as heads. Total number of possible outcomes are either heads or tails, so thus my proportion is going to be 50% or 0.5, or my fraction is going to be 1 divided by 2 in this particular case. Here we're going to work through a lot of different examples associated with probability because it is a fun thing to talk about, but yet at the same time, I don't want to drown out so much of this idea of probabilities that it really bores you or that you don't really gain the appreciation that we have for probability, because it is a very important part associated with statistics. So when we think about probability and we think about sampling in probability, if we want to make sure that we actually use the appropriate definition of probability, we want to make sure that we have this idea of random sampling occurring, right? And again, just to kind of mention this idea of random sampling, I've talked about it already throughout the semester, but here we'll introduce it one more time. Random sampling requires that each member of the population having an equal chance of being selected. So here, this is, sometimes we call it random sampling, randomly sampled, etc. That we'll use that terminology. Don't get random sampling and random assignment confused. Those are 2 very, very different things. Random sampling means giving everyone from the population an equal chance of being selected for the study. Random assignment means giving everyone who you've randomly sampled an equal opportunity of being in any one of our specific groups. So again, with random sampling, we're making sure that we're giving every single member from our population an equal chance to participate. With random assignment, we're giving every single person that we randomly sampled an equal opportunity to be in any one of our groups for our particular study. So that's the core difference between random sampling and random assignment. So make sure you guys always keep those consistent in terms of the way that we explain them. So if we want probability to work, how do we actually want probability to work? In an ideal world, we would want to give everyone from the population an equal chance to participate. So for instance, let's say that you have a deck of cards and you want to know what the probability of us randomly selecting an ace would be. It wouldn't be fair for you to cut the deck in half and then say, okay, then what's the probability of me randomly selecting an ace from the population of the deck of cards? Well, then why'd you cut the deck of cards in half? If you really want to know what the accurate proportion or probability of randomly selecting an ace from the full deck of cards, from the population of the deck of cards, you would want to make sure that all the cards from that deck are actually represented in that stack, not that some of them are being excluded, right? Now, when we think of this idea of random sampling can occur in 2 different forms. Let's say, again, we are doing this idea of randomly selecting a card out of a deck, right? So let's say that we have 4 aces that we can potentially select from, but we have 52 cards, right? Including our 4 aces. So here, one of the things that we would do, let's say for instance, we randomly pull a card out of a deck and we find that it is a king, right? So it's a king, but I don't want a king. I want an ace. So the probability of me randomly selecting an ace from the deck of cards is 4 divided by 52, right? So in our particular case, it's going to be 0.08 if we round off to the second decimal. So 0.08, or an 8% probability or an 8% chance that we're randomly going to select an ace out of the deck of cards. But I randomly selected a king. I didn't want a king though, right? I wanted an ace. So now you have two options. Option number one is to put the king back in the deck of cards. The second option is to kick the king out of the deck of cards since you already randomly selected it. So here, rather than having 4 divided by 52, if you decide that you're not going to keep the king in the deck of cards and now you're going to go for 51, this really is not going to be an accurate representation of the population. Because again, we're already missing one person from the population, in this particular case, one of our king cards. But now here, in terms of us randomly selecting an ace, we should increase the probability of me randomly selecting an ace. So we went from 4 divided by 52 to 4 divided by 51. We go now up just a little bit. So before, it was 4 divided by 52, which comes out to being 0.0769, to now being 0.0784. So we see that it's still 8%, but it's gone up just a tiny bit. So here the probability of me randomly selecting an ace with a smaller denominator has gone up just very, very little. So again, we pull out another card out of the deck and it's a value of an 8, right? So it's the 8 of clubs. So in our particular case, again, I don't want the 8 of clubs. So I kick it out. So now it's 4 divided by 50, and we continue on until we randomly select an ace. So you'll notice here as my denominator gets smaller that we're increasing the probability of me getting an ace because my numerator remains constant in this particular case. But now, what happens in the case where we randomly selected a king, but we still want to give everyone from the population an equal opportunity of being selected? So we want to have random sampling. So in this particular case, what we should do is if we picked a king, rather than going 4 divided by 51, we're going to go back to having 4 divided by 52. So again, we still have the same probability of 0.076, if I remember correctly, in terms of my probability, until again we randomly select an ace. At that time, then your probability is going to change once it is that you've randomly selected an ace out of that deck of cards. So when we think of this idea of probability and sampling, and here let me just delete whatever it is that I wrote there, we also have what's called independent random sampling. And this includes the condition of random sampling and further requires that the probability of being selected remains constant for each selection. So just like we were mentioning here in terms of putting the king back into the deck of cards, this is what independent random sampling really means. That ultimately we're sampling until we get whatever value it is that we want, or we want to know what value it is that we want, but yet we always have the probability of being selected remains constant for each potential selection in this particular case. So in other words, we replace in this particular case that missing value here that we're working with. So ultimately here, what would we do? Let's say that we pull an ace out of the deck of cards. So the probability of us randomly selecting an ace was going to be 0.076. Here, once it is that we do pull the ace, we put the ace back in and we still divide by 52. So again, your probability never really changes in that particular case. So we always have it being exactly at 0.076 or 0.08 if you're going to round off, for randomly selecting an ace out of the deck of cards. So here, once it is that you select the ace, you don't keep it out, you again put it back into the deck itself to again make sure that we're giving the entire population an equal opportunity to participate in this particular case. So let's look at a couple of examples. So again, looking at this example of a deck of cards, if we have 52 cards in our deck, and again here we're excluding jokers in our particular case, and we want to know what the probability of us randomly selecting an ace would be. So if we know that there are 4 aces in our deck of cards, the ace of clubs, diamonds, hearts, and clovers, in our clovers or cloves, I'm not really sure in terms of the terminology, sorry guys, I don't play a lot of poker. But if we have our 4 aces in our deck of cards, if we use our previous formula for the probability of an event, so in our particular case, the probability of us selecting an ace from our deck of cards, we're going to know the number of outcomes classified as our ace. In our particular case, it's going to be 4. divided by the total number of possible outcomes. Our total number of possible outcomes is going to be 52 because those are the number of cards that we have in our deck. So again, we want to make sure that we have the number of possible outcomes classified as A. So in other words, how many constitute or are classified as being an A or an ace in our particular case, divided by the total number of possible cards or outcomes that we have in our deck. In our particular case, it would be 52. So again, the probability of us selecting that ace would be 4 divided by 52, or about 8% in our particular case. So again, we could represent always the probability as being a fraction or a proportion or even a percentage in our particular case, so that way we can identify what that probability of us randomly selecting an ace would be. So again, remember with this idea of random sampling versus independent random sampling. With random sampling, we're giving everyone from the population an equal opportunity to participate. With independent random sampling, now we are pulling a card out of the deck, and we say, for instance, that we actually did randomly pull out an ace, and just by that 8% probability that we were supposed to have, we pulled out an ace out of the deck of cards. You put the ace back in, so now you still have 52 possible outcomes, and your probability has never changed in terms of that idea here that we have, again, 8% in our particular case. So again, when we have the decimals, the probability is going to be represented, or is going to be presented. We can have decimals, we can find percentages. Just remember to move the decimal over 2 places to the right. We learned this in basic math, so that way you can get your percentage. So when we actually have the decimal being represented, like in our particular case here, 0.076, I move the decimal over 2 places to the right, leaving it at 7.6, or I round it off in our particular case and said 8% for our purposes. So when we actually have the percentage then being displayed, and you want to find the probability, or you want to write it as a decimal, all you're going to do is you're going to move the decimal over 2 places to the left. So you're going to imagine that we're actually going to have our decimal being right here next to the 0, and we're going to move it over to the left 2 places to give us that 0.10 rather than 10%. But again, you can represent it however it is that you would like to represent it. For homework assignments or for exam purposes, I'll understand what you mean by the probability in those particular cases. So if we look at a couple of more examples, let's say for instance we want to know the probability of choosing a green marble from a jar containing 5 red, 6 green, and 4 blue marbles. So here we have more of a little bit of a difficult challenge in terms of trying to identify what our specific probability is, because again, now I want to choose a green marble, but in my jar I have 5 red, 6 green, and 4 blue marbles. So here, when I look at the total number of possible marbles that exist inside of that jar, I'm going to add up all of the marbles that I have. So I have 5 red, 6 green, which is going to be 11, and 4 blue, which is going to give me 15 total marbles. Okay, those are total 15 possible outcomes that I could potentially select from that jar. But I want a green marble. So I want to know what the probability of me selecting a green marble is going to be in our particular case. So the outcomes classified as our event, or our green marble, are 6 green marbles that we have in our jar. So 6 divided by 15 should give us a probability of 0.4, or 40%. So in other words, by sticking my hand into a jar of marbles that are made up of 5 red, 6 green, and 4 blue, the probability of me randomly selecting a green marble is going to be about 40%. That's pretty good odds, to be honest with you. I mean, that's pretty good. So if we now look at other options, what is the probability of choosing a jack or a queen from a standard deck of 52 playing cards? So this one's now getting a little bit even more trickier, because what we're now doing is we're saying, okay, we have events classified as 2 possible things here. So the 2 possible things that we have classified here are jacks or queens, because I want to know what the probability of me getting a jack or a queen is. Not just a jack, not just a queen, but a jack or a queen. So now I know that there's 4 jacks in a deck of cards. I know that there's 4 queens in a deck of cards. And again, I have 52 playing cards, excluding our jokers. And also the instructions. So for those of you who are like, what about the instructions? The instructions are also excluded in our particular case. So here I have 8 possible cards, 4 jacks, 4 queens. 8 divided by 52 is going to give me a probability of 0.15, or 15% in our particular case. So here, if you've noticed now, from our example of the aces versus the example of the jacks or the queens, the probability of me getting one of these cards has increased from 8% to 15%. Think about that. Why does that happen? Why has the probability gone up from me being able to only randomly select 4 aces from my deck of cards, or now selecting 4 jacks or 4 queens. So why is it now that the probability has increased? The answer here is we've increased the numerator. We've increased the possibilities, or sorry, we've increased the outcomes that we classify as our event. So in other words, we classify now our event as being jacks or queens. That number has gone up from 4 aces, to now saying jacks or queens. So I'll take either jacks or I'll take queens. It doesn't really matter. So I've increased that numerator. I've increased the outcomes classified as my event in our particular case. Thus, increasing my numerator and keeping my denominator constant is going to increase the likelihood of me getting a higher value. So remember from basic math that when we use the following in terms of fractions: 1 divided by 4, 2 divided by 4, 3 divided by 4, and 4 divided by 4, you'll notice now that as the numerator increases and the denominator remains constant, that my value goes up. So 0.25, 0.50, 0.75, and a value of 1.0, right? So my numerator has increased, my denominator has remained constant. In our particular case, when we had 4 aces divided by 52 cards, my numerator is quite small in comparison to my denominator, but now I have 4 jacks or 4 queens, so 8 divided by 52, increasing my numerator, my denominator has remained constant. So now thus why I go from having 0.076 to now having 0.15, because again, I've increased my numerator, increasing the likelihood of me selecting a card that I want. So now let's say, well, what happens in the case where I want to select a high card, okay? It can be a jack, queen, king, or ace. Jack, king, queen, or ace. So I have 4 jacks, 4 queens, 4 kings, and 4 aces. So that should give me 16 cards that I should be able to select from, divided by 52 in our particular case here, because again, remember, we have 52 playing cards total, now increases the likelihood of me randomly selecting a card that I want at 30%. So here, I'm pretty good, or even 31% if we round off to the second decimal point. So we may be at 31%. So here you'll notice that once it is that we start classifying more events as being the ones that we want, and our number of outcomes remains consistent or constant, our overall proportion or probability of us randomly selecting an event such as our own that we want it to be is going to increase in our particular cases here. Now, many times what you're going to find is that finding the probability of a score in a particular data set is going to be very important for us. So let's say, for instance, that we have a frequency distribution that looks like the following here. I've taken this frequency distribution from your textbook, so if you're following along with your textbook reading, this is one of the figures in your textbook. I can't really remember which one. It's, I think, maybe 6.3 or 6.4 of one of your figures. But if we look here and we want to say, okay, what's the probability of me selecting a value of a 5 or greater? So here, if you'll notice now, when we have our frequency distribution, remember that on our y-axis, we have our frequency of occurrence of each one of my values in my data set. And on my x-axis, I have my values for my data set. So in other words, here's my value of a 1, 2, 3, 4, 5, 6, 7, and 8. You'll notice that 7 and 8 don't have any boxes, thus because they did not occur in my data set. So even though there were options available for people to select, they did not get selected, or they were not represented in my data set. So here, if I want to know what my total number of scores are in my data set, I'm going to count up my boxes in my particular case, right? Or I can go to the height of each box to identify the frequency of occurrence. So in our particular case here, a value of a 1 occurred 2 times, 2 occurred 1 time, 3 occurred 2 times, 4 occurred 3 times, 5 occurred once, and 6 occurred once. So my sample size in my particular case is going to be 2 plus 1 is 3, plus 2 is 5, plus 3 is going to be 8, plus 1 is 9, plus 1 is 10. So my sample size is 10. So here, for instance, I want to know what the probability of me selecting a value of a 5 or greater is going to be. So I want to know what the probability of that having occurred in my data set is supposed to be. So I know that the total number of outcomes that exist in my data set are 10. I want to know 5 or more. So here in our particular case, we know that 5 occurs one time, 6 occurs one time as well. So the probability of our event, right, or our outcome classified as 5 or 6 is going to be a value of a 2 divided by the total number of values in my data set. In my case here, there's 10. 2 divided by 10 is going to give me 0.2 or 20%. So in other words, what's the probability of someone getting a value of a 5 or getting a value of a 6 in my data set? It's 20% or 0.2. Okay? That's what we're talking about here in terms of our probability. That I'm now able to identify such things as what's the likelihood of this value. All right, so now let's switch gears and talk a little bit about trying to find the probability of a score existing in a data set whenever it is that we want to know the proportion of the probability of a score having occurred in my data set, but without necessarily knowing how many scores occurred in my data set as a whole. So in this particular example here, we knew exactly how many scores occurred in my data set, and we knew exactly what my scores is that I had of interest. So I knew that I wanted to have scores that were 5 or greater, and I knew that I had 10 total scores. But what happens in the case where I don't know how many total scores I have? But rather, I know a couple of key pieces of information. I know the mean, I know my score, and I also know the standard deviation. So in your textbook, you may have come across this particular table here, and this may have confused you a little bit. This table is actually on page 173 in your textbooks, and you may have noticed this and said to yourself, I have no idea what this table is, and it's very, very confusing to me. Today, what I want to do is I want to go through this table very briefly here and show you an example of how useful this table actually is for us in terms of trying to identify the probability of values occurring in our data set, or the likelihood of specific values occurring in our data set. So you'll notice here in this particular table, you have columns labeled A, B, C, and D. Now what I've also done is in Blackboard, I've uploaded for you this particular table that's called the Statistical Tables Unit Normal Table, which is exactly this table that's represented here. Given to you, but now with all our values in our actual table. Now, since both of these tables are useful to us, I'm going to be referring to this particular table here in terms of our example. So, in terms of this particular table, what is it that this is used for? This is a unit normal table. In other words, this is a distribution of z-scores. And I know you probably don't want to hear that and say z-scores, I thought we were totally done with that last week, but why are you talking about it again here? I do apologize, but unfortunately I have to talk about z-scores for just a little while longer. So here with z-scores, z-scores are very, very useful for us because they convert everybody on this standard distribution. So if you remember from my discussion from last week, one of the key arguments or one of the key points that I make in terms of our discussion of z-scores is that you can take now apples and oranges and compare them on the same distribution because you're all talking about the same idea, this idea of z-scores. So ultimately what we're going to do with this particular distribution is we're going to identify where a z-score exists for a specific raw score from my data set and then try from this distribution to identify the probability of a value such as the one that I want, right? So such as my z-score or higher occurring in my data set. And that's what I really want to look at in our particular case. So ultimately, when you look at this table, you're going to notice that we have column A, which is our z-score, right, that we're going to calculate. B, which is the proportion in the body. And here, that's this shaded area here that's labeled B as in the body. Proportion in tail, which is this area that's not shaded that has the letter C. And then also proportion between mean and z. So the ones that are really going to be of interest for us for today are going to be these two here, which are going to be column A and column C, which are going to be the ones of primary interest for us. So what we're going to do is we're going to look at the following example. So let's say that we want to think of an exam, such as the SAT score or the SAT. So let's think of the probability of a score being a 700 or greater on the SAT. Now I've taken this example from the one that's in your textbook, so if you can follow along with what's in your textbook and with what's here, and you're able to understand how it is that I came up with this idea of the probability for these scores, we should be okay in terms of our discussion. If you're still having some issues, revisit the lecture, revisit the textbook discussions to really get a firm grasp on this idea, because it is important for us. So let's think, what's the probability of someone getting a 700 or a greater on the SAT? Now, to be able to answer this question, we need a couple of key pieces of information. Number one, I need to know what the mean for the distribution of SAT scores is. Two, I need to know what the standard deviation for the distribution of ACT scores are. And last, I need to convert my raw score of 700 into a z-score. And in our particular case, the minimum score that I'm looking for is a 700. So whatever my z-score value is, that z-score and above is what's really going to be of my concern. That's what I really want to be interested in. I want to know what the minimum value is that a person needs to get, and then anything above that, and then find the probability of them getting that score. Okay, so what I need to do is I need to convert this value of 700 into a z-score, and then that z-score and anything above it, I'm going to be able to calculate the probability for it, because that's what's of interest to me, because I want to know what's the probability of someone getting a 700 or greater on the SAT. So here, remember that for our formula for z, remember that our formula is z equals my score minus my mean divided by standard deviation. The population formula, remember, it's the exact same thing, just with a couple of different terms. So the score minus the population parameter associated with the mean, so mu, divided by the population parameter associated with standard deviation, which is sigma, but both formulas say exactly the same thing, just one's for a sample and one's for a population. So one's a stat and one's a parameter. So ultimately here, I want to convert this 700 into a z-score. So I'm going to take 700 minus my average, which I'm going to say my average is 100, or my average is a 500, and my standard deviation is a 100. So now if I do my calculations, 200 divided by 100 is going to give me a z-score equal to positive 2. Okay. So now I know what my z-score is going to be equal to. So now what I want to do is essentially my question changes just a little bit. I now want to know what's the probability of someone getting a z-score equal to a 2 or greater. Okay? So essentially this means the exact same thing as here, because all I've done is I've converted this 700 into a z-score. Okay? So now if we look back on our table, what I want to do is I want to find in this column here, my A column, my z-score. So I'm going to go all the way down until I find my z-score of a 2. So here it is. So I want to now, I try to identify the following piece of information. What is the probability that someone is going to get a score of a 2 or greater in terms of the SAT, in terms of z-scores? So ultimately here, you'll notice that we have this proportion in tail. The proportion in the tail tells me the probability, and in this particular case, the probability of the minimum cutoff or greater. So in other words, if this is my distribution, to the best of my drawing abilities, where I have a minimum cutoff of a value of a 2 as my z-score, because remember, that's what my value was in terms of a 700. So remember, this represents a 700 for my score, and this represents a 2 in terms of my z-score. I want to know now what's the probability that someone will get a 700 or greater in terms of their SAT score. Because remember, if this is a 2, this line represents a 2, anything to the left of it is going to be less than a 2, right? So we're going to be getting further away from this value of a 700. So we're going to get values into 650, 600, 650, and, or 550, etc., right? So here I want to know what's the probability of someone getting a 700 or greater on the SAT. I've converted my 700 into a z-score. My z-score now becomes a value of a 2 for this particular distribution with a mean of 500, and my standard deviation equaling 100 in our particular case. So I've calculated my z-score equaling to a value of a 2, so now I use the 2 as my minimum value, and what's the probability of someone getting a value of a 2 or greater in terms of their SAT score? So now you'll notice here, we have this value here of 0.0228. That is the probability that someone will score a 700 or greater on the SAT. That's how we're going to interpret that number there. So how did I come up with that number? Again, I went through the column, I found my z-score that corresponds to my raw score. In this case, it's a value of a 2. I find the proportion of the tail, because remember, this is now going to be considered the tail. This is the body, right? This was what we categorize as letter B. This is what we categorize as letter C. So in our particular case, we're saying in this area, the proportion of the tail, where we have a minimum value of a 2, what is the probability that someone's going to get a 700 or greater or a z-score of 2 or greater in terms of their SAT exam is going to be equal to 2.28%. So that's our answer. That's the probability that someone will score a 700 or greater in terms of their SAT. Now, even though this represents a z-score of a 2, we still interpret it as being in reference to my raw score of 700. Okay, and that's a very, very important thing to consider, that even though this is in reference, this probability was in reference to a z-score of a 2, we're still talking about it in terms of my raw score, because remember, your z-score corresponds to a raw score in our particular case that we're discussing here. All right, so before we end today's lecture, I do want to cover just a couple of more problems associated with finding the probability of a score occurring in our data set or occurring for our given exam, for instance, aside from the example that I just provided with you earlier. So let's think of another example. So here we had covered the example associated with SAT scores getting a 700 or greater on the SAT, just following along with the example that's in the book. But here I've created 2 additional examples for you so that way we can follow along and try to use them and try to understand how probability tables work for us, and in terms of using our unit normal table to find exactly what the probability of our scores are going to be. So in this particular case, let's take the following problem. What's the probability of a score being a 50 or greater on an exam? So just as we did in our previous example, here we're trying to find what the minimum value is, and then we're trying to identify what's the probability that scores are going to be that minimum value or greater in terms of our exam. So just as with our previous example, I need to know a couple of pieces of information. I need to know the mean and the mean for the distribution of exam scores. I also need to know the standard deviation for the distribution of exam scores, and I also need to know the z-score for my minimum value. So in this particular case, my minimum value is a value of a 50. I need to convert that value of a 50 into a z-score. So again, if you're wondering why is it that we are converting our value into a z-score, why can't I just look at the scores in my data set and say, okay, how many people actually got a 50 or greater on the exam? Well, the idea is that I may not necessarily know everyone else's score, and I may not know how many people were even in my data set. So I may only want to know what my minimum value is, and then greater above that minimum value, beyond that threshold of a 50, but I may know the mean, I may know the standard deviation of the distribution for the exams, thus allowing me to still calculate the probability. So here I may have some unknown values or unknown factors in the case of I don't know what my sample size was, and I don't necessarily know what everybody got in terms of the exam. I only know what my minimum value is going to be, and then I want to know what everybody scored above that, or the probability of people scoring above that minimum value and greater. So again, here I need to know my mean and also my standard deviation for that specific distribution of exam scores. So here, let's take an example of this. So in our particular case, let's assume again that my score is going to be a 50 or greater, right? That's what's of interest to me. And I know that my mean for my distribution is going to be a 75. And here, these are just values I've made up for you, so don't ask me where is it that you got that mean from. It's just a value I made up for our purposes in terms of an example. My standard deviation in our particular case is going to be a value of a 13. Okay? So in our particular case, we need to convert my x value, my minimum value of a 50, into a z value. So again, using my z formula, so again, taking my score minus my average, dividing it by my standard deviation, I'm going to take my value of a 50, which is my minimum value, minus 75, divide that by a value of a 13. So when I do my calculations, this should give me a negative 25 in the numerator. My denominator should remain a value of a 13 because that's my standard deviation. And now my z value for a value of a 50, right? So for my raw score of a 50 is going to equal, if I'm not mistaken, negative 1.92. So 25 divided by 13, or negative 25 divided by a value of a 13, should give me a value of 1.92 negative in our particular case. So here I'm correct in terms of our z value. So in other words, I now know what my lowest value is in terms of my data set, right? In terms of my minimum cutoff. So here on this distribution that I've created here for us, this is a representation of the distribution that we have from our unit normal table. So again, referring to our unit normal table, I've essentially just drawn this distribution for you. I've located the 0 because the 0 is going to be the average for this distribution, as we talked about in our z lecture last week. So here I now need to find that area where we're going to have 1.92 beginning, or that point at where we have 1.92 beginning. So in our particular case, one of the things that you'll notice in terms of our unit normal table, and in your textbook it made note of this, that the unit normal table, since it's a symmetrical distribution, it's going to assume that whatever's to the right of the distribution is going to be the same as to whatever to the left of the distribution. The only thing that changes is the positive or the negative values. So on this side we're going to have positive values, on this side of the distribution we're going to have negative values. So if you notice here on your unit normal table, you only have positive z values that are actually found in terms of this column for column A. But you notice that we don't have any negative values. The idea here is that it doesn't really matter if we have positive or negative values. All that you would need to do is go and find your z value. In our particular case, it would be a value of 1.92, and then we would just apply a negative to it. So in other words, rather than looking at the right side of the distribution, which would be the positive sides, we would then look at the left side of the distribution and identify where 1.92 would exist on my distribution. So in our particular case here, I've drawn that distribution for you. And here I'm just going to go ahead and just kind of, eyeball wherever 1.92 would be. And here it doesn't really matter where it is that I put 1.92, because what I'm trying to calculate is I'm trying to calculate the proportion in the body and then the proportion in the tail for our specific example here. So here I'm just going to say that 1.92 was somewhere along this continuum. And here, let me see if I can get this going. Here we go. Whoops. Okay, give me 1 second. Okay, sooner or later I'll be able to write. Here we go. So we're going to say that this is going to be my value of 1.92. Okay, so this is z equal negative 1.92. How did I identify that that was negative 1.92? I just looked on the negative side and I arbitrarily wrote on here 1.92 in our particular case. If I wanted to be more exact, I would find the 1 standard deviation portion, I would find the 2 standard deviation portion, I would try to calculate 1.92. But for our purposes here, we're going to be okay if we just write out and have our line that we've drawn and say negative 1.92, because it's more important for me to know that it was on the negative side, not necessarily on the positive side. Okay, so here's one of the things that's going to be a little bit confusing about this problem. So this is a tricky problem when you think about it. When we looked at our previous example about 700 for being our SAT score, the mean for our distribution, if I'm not mistaken, was a value of a 500. So any value above the value of a 700 was going to remain positive. So if you remember on this example here that we had done, we had said 700 minus 500 divided by 100, because that was my standard deviation. So it was 200 divided by 100, giving me a z value equal to a value of a positive 2. So let's assume here that a person doesn't get a 700, but they got an 800. So 800 minus 500, divide that by 100, now gives me 300 divided by 100, giving me a z-value equal to a 3, positive 3. So you'll notice here that my z-value gets larger in the case where my score gets larger, right? Because I'm further away from the mean in this particular case, higher above the mean in this particular case, right? So as my score continues to increase from 700 to 800 to 900, my z-score is also going to continue to increase because I'm getting further away from the mean in terms of standard deviations. So in this particular case, I'm only 2 standard deviations above the mean. Here I'm 3 standard deviations above the mean. If my score is 900, 900 minus 500 is going to give me a value of 400. 400 divided by 100 is going to give me a z-value, excuse me, a z-value equal to a positive 4. So we'll notice here that we start getting further and further away from the mean. So here, my value in terms of this distribution that I had drawn for you, we would draw our line for 0. So here was the value for a 2. Here was the value for a 3, here's the value for a 4. So you'll notice that I start getting further and further away from 0, so the probability of people getting a 900 or greater on the SAT starts getting smaller and smaller and smaller, because this portion, after I've identified my z-value, right, so this critical value right here that I'm going to call it in this particular case, once I've identified that location, anything to the right of that area is going to be the body in the tail, or sorry, the proportion in the tail. So thus, it's a very, very small area. So the probability that someone's going to land in this area is going to be very, very small. So here, as my z-score got smaller, closer to 0, you'll notice that the area starts getting larger. So in other words, more people can actually land in this area, right? So as my z-score gets larger, less people can get in there. So the probability of somebody getting a 900 or greater is going to be smaller. But if someone gets an 800 in comparison to 900, there's a higher probability that people are going to get that score. 700 versus 800 versus 900, more people are now going to have the probability of landing in that area, right? So now here, we go to this example where we now have the probability of a score being 50 or greater on the exam. But you notice here that in my particular example, my average is a 75. So this is the tricky part of our question. So here, if a person gets a 50 on the exam, that's the minimum value, right, that we have, and the average is a 75 and standard deviation is a 13, my z-value becomes a 1.92. But now what happens in the case where we say, well, we want, again, remember the probability that people are going to be a 50 or greater. So here, let's calculate for a 60. So 60 minus 75, divide that by a value of a 13, is going to give you negative 15. Divide that by 13. So 15 negative, divide that by a value of a 13, is now going to give you a z-value equal to a negative 1.15. Now you're probably asking yourself, well, wait, what happened here? Why is it that my z-value got smaller than it was here if my value down here, my raw score of 60, is larger than my raw score of 50? That is true. That's a very good question. And the answer is the following. Look at the value in comparison to the average. Here, the distance between my raw score and my average was 25 points. Here, the distance between my raw score and my average is 15 points. So the gap between my raw score and the average is getting smaller, right? Here, it was a lot larger. So since it's getting smaller, I'm getting less far away from the mean. So thus my z-value is going to get smaller in comparison. Because remember, what does a z-value tell you? A z-value is going to tell you how far from the mean your score is in terms of standard deviations. So here, since my raw score is larger than it was here with my value of a 50, my z-score is going to be smaller because the gap is getting smaller in this particular case. In our example with the SAT scores, when we went from 700 to 800, my average was a 500. I was getting further away from the mean. So from 700 to 500, that's a difference of 200. 800 to 500, 300 of a difference. 900 to 500, 400 of a difference. Thus why my z-value got larger in that particular case. So here, my z-value is getting closer to 0 in this particular case because my value, my raw score, is getting closer to the mean. Now, it's only negative because remember, again, my raw score is below the mean in this particular case. So in our case here, we've noticed that now with the z-value for a raw score of 50, so where x equals 50, and now where x equals 60, my z-value then is going to be somewhere here. Oh. No, I still can't get it to right. So this is going to be my z-value equaling to negative 1.15. So for my raw score, equaling 60. Okay, because I'm getting less further away from the mean. So I'm getting closer to the mean in that particular case. Okay, so in our particular example, remember what my example was requesting, or what my question was. What's the probability of a score being 50 or greater on the exam? Okay, 50 or greater on the exam. So again, I needed to know the mean. I already know that, which is a 75. I know my standard deviation, which was a 13. I've converted my minimum score into a z-score. I've converted another score in our particular case here just to show you that a larger value is getting a z-score that's lower. So in other words, this is where the tricky part begins. So the negative 1.92 is the minimum value for a 50. What is beyond negative 1.92? What's beyond negative 1.92 in terms of a raw score? Is it going to be greater than 50 or less than 50? So let's try that out. What happens when my score is a 40? 40 minus 75, divide that by 13. So 40 minus 75 is going to give me a negative 35. Divide that by a value of a 13. Is now going to give me a z-value equal to a 2.69 negative. So in other words, it's further away. So here, my question wasn't, what's the probability of me getting a 40 or less? The question was, what's the probability of me getting a 50 or greater, right? So here, in reality, this line here that represents my raw score of a 50 is my minimum value, and everything to the right in this area here, in this particular case, is greater than 50. Okay, and I know that sounds weird that you're like, what? Like, how is that possible? Like, we kept looking at column C, at the proportion in the tail. Now you're telling me to look at area B, the proportion in the body, because that's what I'm telling you to do now. I'm telling you to look at this area here, right? So think of this as being my 1.92. This is less than a value of a 50 in terms of a raw score. So here, if you want to draw this out, we're going to say that this is going to be my raw score of a 50 in our particular case. This is going to be a value of a 40. This is a value of a 60, etc., etc., etc. So over here, let's assume it's going to be a value of a 90. Okay, so here is my minimum value. This is what's greater, okay, than my minimum value of a 50. This is lower than my minimum value of 50. So now, rather than looking at this area, I'm telling you no longer look at that area. So don't look here. You're now going to look here. This is what I want you to look at in this particular question, because the question is asking you the minimum values of 50 greater than 50. Now, what's the probability of that? So again, I still have to go and find my minimum value of a 1.92. So again, we had circled 1.92, so it's right here. And now, rather than looking at column B, in our particular case, okay, give me 1 second here, guys, sorry. So rather than looking at column C, the proportion in the tail, because remember, in now our example, the proportion in the tail are values that are lower than a 50, we now need to look at the proportion in the body. So values that are going to be 50 or greater. So what's the probability that people are going to score a 50 or greater in our exam? In our particular case, it's going to be a 97.26% probability that people are going to score 50 or greater on the exam based on our average and our standard deviation. And again, why does that happen? Because again, 50 is my minimum value here, right? That corresponds to a raw score of 50. My z-score is a negative 1.92. All of this area represents values that are greater than 50. So here, what's the probability? There we go. Probability of getting a 50 or greater on the exam when the average is a 75 and standard deviation is a 13. The probability equals 97.26%. So that's the answer to our question in our particular case here. So here, rather than looking at the portion in the tail, I'm now looking at the portion in the body. So it's a very tricky question, and I know you're probably thinking about it, you're like, okay, now I'm totally confused. So why in one was I looking at the tail, and why in another one was I looking at the body? Again, that depends on how far your score is from the mean. So here, if your scores are above the mean, then you're going to be looking at the right side, and you're probably going to look at the tail. If your scores are negative and you want to know what the minimum score is or greater, you're not going to look at the tail, you're going to look at the body. Okay? Because now the portion of the tail are going to be scores that are going to be lower because they're going to be on the negative side. So they're getting farther away from the mean but lower. So in our particular case with our SAT scores, we were looking at the portion in the tail because our values were positive, thus indicating that our raw scores were above the mean in that particular case. So let's try out one additional problem here. And here I just noticed I made a mistake here, so ignore the fact that this is 50 here. My minimum score is going to be an 80. So what's the probability of a score being an 80 or greater on an exam? So here we're going to use the exact same average. So my average is still going to remain a 75. My standard deviation is still going to be equal to a 13, but now my minimum score is a value of an 80. So what's the probability of someone scoring an 80 or greater on the exam? So now let's go ahead and identify that in terms of our particular problem here. So here, let me just have another page open for you because I've noticed that I've just written all over this here. So give me a second here and let me insert an additional page. Okay, so here's our additional page that we'll work on for today. So again here, I have my distribution again, right? So again, the mean for this distribution is going to be a 0. My equation again, remember for z, is my score minus my mean. Divide that by standard deviation. In our particular case, my score is equal to a value of an 80. My mean is a 75, and my standard deviation is equal to a value of a 13. So here my z-score for my minimum value in this case is 80 minus 75. Divide that by a value of a 13. So 80 minus 75 is a value of a 5. Divide that by a 13 gives me a z-value equal to positive 0.38 in our particular case. Okay, so here on my distribution, I now want to identify where z positive 0.38 is. So I'm going to say it's probably going to be somewhere around here. Okay, so positive 0.38. So that there corresponds to a z equaling positive 0.38. So again, how did I come up with positive 0.38? Again, I took my score minus my average divided by my standard deviation to give me that particular value there. So here I knew that my z-score should have been positive because my raw score is above the mean. That automatically tells me that's a positive value. Dividing it by 13 in this particular case, which is my standard deviation. So here I'm still using the exact same mean and standard deviation that we had in our previous example, just so that way you can see the probabilities going from a very low score to going higher, and now a high score going higher in our particular case. So we want to know what the probability of someone getting an 80 or greater is going to be. So again, I now know what my z-value is, so positive 0.38. So now in this particular case, this now becomes the body of my distribution. So all of this side is the body, and this is my tail. Okay? So why am I now going to look at the tail of the distribution? Because this line here represents the minimum cutoff of an 80, and anything beyond this point in terms of this line, anything beyond 0.38 positive is going to be a higher value. So again, let's calculate it for a 90 minus a 75, divide that by 13. So our value is 15 divided by 13 is going to give me a z-value equal to a 1.15. So you'll notice here that now when my raw score is a higher than an 80, which is a value of a 90, it goes further away from the 0 to the right. So in other words, it's now going to appear somewhere around here in our particular case. Okay, so this may be my z equaling 1.15 in our particular case. Okay, so here again, this area from right here on is going to be my tail. That's what I want to look at. So again, I'm going to go back to my unit normal table. I now want to go and I want to identify 0.38 because that's my z-score. So there's 0.38. So now here, what do I want to look at? Do I want to look at the body or do I want to look at the tail? Well, I don't want to look at the body because those are lower values. I want to look at the tail. So this is what I want to look at now in this particular case. So here, I'm not going to look at portion in the body. I want to look at portion in the tail. Okay? So here, what's the probability that someone is going to score an 80 or greater in terms of the exam? According to my table, the probability of someone scoring an 80 or higher in the exam is going to be 35% or 35.20% in our particular case here. Okay? And why? Because again, I've identified that minimum value in terms of the tail. So I've converted that raw score into a z-score, which becomes 0.38. And then beyond 0.38 is the area where I want to see that people may land in there. So what's the probability of somebody landing on a 0.38 or above? According to my unit normal table, it is 35.2%. So that's the probability of someone scoring an 80 or greater on the exam. The probability equals 35.2%. So here I've used the exact same mean, the exact same standard deviation, so that way you can now identify what portion of the distribution you're going to look at if your scores are low in terms of the average, right? So here your value is below the mean. So here having higher scores is still good, right? In the case that we want to see what the probability of someone scoring a 50 or greater is going to be, but do realize here that you're not going to look at the tail in that in this particular type of problem, because again, remember, your scores are getting higher, they're getting closer to the mean, so here they're going to the right. So we want to see this area in the body in that particular case, and we're going to ignore the tail. Here, my score is already above the mean, so here I'm on this side of the distribution. So in this particular case, anything that is on this side of my value here of this critical z value, if you want to call it that, is going to now be considered the area that I want to look at. In that particular case, that becomes the tail, and I want to look at the probability of our scores landing in the tail if my z value is 0.38 as my minimum cutoff value. So hopefully these examples have helped you a little bit more in terms of your understanding of how to identify the probability of us having scores occur in our data sets. And in this particular case, I've given you some examples associated with finding the probability of having a minimum score and then scores that are above that. And in both cases here, I've given you the cases where our raw scores are below the mean and we're going higher. And then in our second example here, we have our raw score already being above the mean, and we want to still go higher in terms of our raw scores. So finding the probabilities for those particular types of values. Please let me know if you do have any questions. Remember that your homework assignments are due this Friday, so please make sure to turn them in appropriately or on time. If you notice in terms of the homework assignment, I've given you a couple of questions from the homework assignment that have the answers in the back of the book. I know that the answers come in the back of the book for the odd values or for the odd questions. So here, that's okay if you guys take a look at those and you want to confirm your work. I still want to see your work, so it's perfectly fine that you look at the answers in the back of the book after you've done the work. If your answers are not coming out to what the answer is, try again. Try your question, or try your answers multiple times, or email me and I'll be happy to answer any questions. Have a good rest of your week. Please don't also forget to answer the discussion board post that is going to be due on Friday. That's your initial post, and then your rebuttal or your comment to somebody else is due by Sunday by 11:59 p.m. Have a good rest of your day, and please make sure to look over the lecture if you have any additional questions or contact me.